The electroscope is a fairly common physics apparatus used in introphysics to teach you about charges. Now, the unfortunate thing is that you probably haven't interacted with one before, or at least you haven't interacted with one outside of the physics classroom. So I have to spend a little bit of time explaining it so that every time it's used to explain charges, you have some idea what's going on. The basic idea is that you have a metal contact on the outside. It's usually a sphere, but there's nothing special per se about it being a sphere. And then there is a metal connection down to gold leaves. And leaves in this case doesn't mean that it comes from a gold tree, but simply that it's really thin, light pieces of foil. Now, this doesn't have to be gold, it could be silver, it could be aluminum, it just has to be a really good conductor and really, really light. Now, the reason it's in a box is to try to isolate these so that air moving across it doesn't disturb it. So this is the cartoon picture from your book. This is then a real picture of one that's actually built inside a flask. So again, you can see these are the leaves down here. They're not gold colored, they're some sort of silver, and they're just connected to a metal thing that comes up to the end. So again, it's sealed not because it has any special gas inside, but simply so that air and humidity doesn't come in and disturb it. So what we are then looking for is when these two leaves repel each other. And these are going to repel each other if they have the same charge. Why would they have the same charge? Well, for instance, maybe there's a net charge on this whole thing. Because this is all metal, we expect that the net charge will in fact distribute, and then you have the same charge, either positive or negative on both of these, and you get a repulsive force. So an example would be, for instance, if you had a charged balloon. Balloons frequently will remind us of static electricity, which is kind of what we're talking about right now. And you touched it to this such that you transferred some charge. You would then imagine that charge distributing itself over this entire metal component, and then these two leaves push each other apart. So this is something we'll look at in lecture, but the book is going to show you pictures of it, so it's helpful to go through this and understand it. So a diagram of what would be happening here in detail if we bring in a plastic rod, and note that here we're not showing the box, but again there's some sort of isolation just to better for the experiment to work better. The plastic comes into contact with the metal, so you transfer some of the charge, but since this is all metal, it's a conductor, the charge distributes itself into electrostatic equilibrium, and now you have negative charges on each of the metal leaves. These are able to bend away from each other. They're very thin, very light, so they push apart, and we see them pushed apart like this. We know that there's some sort of force pushing them apart. Now, there would, for instance, be a little bit of gravity down and some tension, but normally they would just hang. So this angle indicates that there is some sort of force. So that's what we're looking for. We're going to do some slightly fancier things with it as well. The second thing we can do, the fancier thing, is polarizing it. And polarization is a little bit tricky, and this might be a new concept for you. So the idea is that we're going to bring something in and we're not going to touch it. So note that this air gap here is real. So this is a glass rod that has been rubbed with silk, so it has positive charges. And now keep in mind that the metal has both positive and negative charges in it. Initially, the electroscope is neutral, but we have this positively charged rod, which is going to attract the negative charges in here, i.e. those electrons in the sea of electrons. And you can think of this as actually repelling the positive charges. Now, we don't necessarily say that the metal ions themselves are moving around, but you can think then that the farthest away is where you're going to have the biggest positive charge. So we have an excess negative charge on this surface near the positive, and we have an excess positive charge on the surface away from the positive. Now again, this is still neutral. We have 6 negative charges here and 6 positive charges here. So it's totally still neutral, but it's become polarized. We have separated the negative from the positive. So note that in this case, the metal leaves do push away from each other. And the reason for that is they again have the same charge. But in this case, it is simply due to polarization. So I think that this can be one of the trickier topics to understand since it might be new, and because especially if we talk about the electroscope, we can see that these two leaves repel each other either due to a net charge, an excess charge on the entire electroscope, or simply due to polarization. Now, with polarization, if I removed my glass rod, we would then see the leaves pretty much immediately come back together because these negative charges would then come back down and redistribute. So that's one of the things about polarization, that as soon as you remove the polarizing object, this external charged object that is not touching, the charges immediately go back together. So that's kind of the basics of the electroscope. Again, it's used as a tool to understand other charged phenomena, but in it itself takes a little bit of understanding.